Okay, so this is in my notes as section 14.4. This is actually section 14.3. So remember early on when we were looking at plots of concentration versus time. And they were kind of curved. We had started with the reactant and we watched how it went away. Well, I mean, there's some information that you can get from that type of plot. But we can also do some mathematical manipulations to be able to determine the concentration as a function of time. And it actually makes some of the math later on a bit easier. And so that's why we use this, what's called integrated rate laws. So we saw the piece early on where we were finding delta concentration over delta time. And so that's an average for a given time period. Now we're going to find that instantaneous time. That's what we're doing here with integrated rate laws. We have different orders of reactions that we can use integrated rate laws for. And we're going to look at 3 different ones. A zero order reaction, first and second order reaction. Okay. For each of these, we see these integrated rate laws, which you will get on the exam. Excuse me. You see 4 different variables. We see an initial concentration, so that's A in brackets, so the concentration of A, subscript 0, that stands for initial. You may also see sub I. And then concentration at another time is just going to be concentration of A, or sometimes concentration of A sub T. Right. We'll see our rate constant K, and then time is going to be T. Okay. So the first order integrated rate law is given here. Okay, so now we have natural log ln of A at some time t equals minus kt plus the natural log of A sub 0, our initial concentration. We could go through and determine how these, work through the math to figure out how these equations came about, but I'm not going to derive those for you. I don't think that's very invigorating. And so it's boring. We're not going to do it. I don't even know if it's in your book, actually. But second order is a little different. Okay, second order is 1 over A sub t. So it's a 1 over equals K times T, positive, plus 1 over A sub 0. Okay, so second order has fractions. And then zero order probably looks the most user-friendly. It's A sub t equals minus K times T minus, hang on. Shoot. Plus A sub 0. I think I forgot a plus sign in my notes. Okay. Yeah. Okay, like I said, you will be given these on the exam. One of the reasons why integrated rate law expressions are useful is that they're all in the form of y equals mx plus b. Okay. So we can make straight line plots for each of these, but I first want to write out y equals mx plus b on each of these so you can see what factors go where. Okay, so again, we're basically fitting to a line. Some will be positive, some will be negative. When we plot these, we're going to have some form of concentration on the y-axis, and time is going to be on the x-axis. So time is always going to be x. Right? So for our zero order, A is going to be y, B, our intercept, is going to be a sub 0. The slope is going to be minus k. And x, of course, is t. So intercept, the y-intercept is a sub 0, and the slope is minus k. So this one will have a negative slope. Okay, and our y-intercept is our initial concentration. So it's going to be somewhere high with a high value, right? Whoop. And the slope is going to be negative. On y, we're going to have concentration of A at whatever time. And of course, time is on x. Questions on that? Okay. For our first order, we're going to have y is ln of a. Our intercept is natural log of a sub 0 minus m. So our slope is minus k, and then x, of course, is t. So if we plot this, we're going to have natural log of a on the y-axis, t on the x-axis. Again, a negative slope. The y-intercept is going to be natural log of a sub 0. Okay? So why am I going through all of this stuff? You can use a plot of kinetic data to determine if a reaction is first order, second order, or 0 order. So that's what this is, where this is coming from. Second order is the only order reaction with a positive slope for the integrated rate law. Y is going to be 1 over the concentration at some time. The slope equals k, positive k. And the intercept is 1 over the initial concentration. So if you think about taking 1 over some number, okay, what's that going to look like? I'm going to make that number look smaller. And then positive slope here. Questions on that? Okay. So if we didn't use integrated rate laws, they would look something like this if we plotted concentration versus time. Okay? 0 order, first order, second order. All right? It is a little bit harder when this math was being done by old people who didn't have computers to work with exponents. These are all exponents. Okay? Now we can make things into linear equations. That makes things much easier to work with. They're still visually easier to think about, I would imagine. But this is why we're doing this. Okay? We're changing from a plot that is an exponent, slightly harder to sort of grasp, and changing it into a linear equation. Okay, so for our 0 order data, remember that for 0 order, A at some time t equals A initial minus k times t. We're going to draw 2 lines initially, okay? where both of the data are for 0 order. So we're going to have time on our x-axis and a sub t on y. But they're going to have two different rate constants. Okay? Now remember, the rate constant is equal to the slope. So if they have the same initial concentration, but a different rate constant, take 15 seconds and think about what that might look like. I know that's not enough time, but we'll try. Okay, so if we have the same initial concentration for our two plots, we'll start at some point. One will slope down like this. It has some value of minus k, and the other might slope down like that. And we can never mind, we can't do that. I was going to try to differentiate that, but it doesn't matter. That represents two different rate constants. Same starting concentration, two different rate constants. If we want to add another set of data with a different starting concentration, but say the same rate constant as this one, okay, we could do something like this. So the slope is the same, it just starts at a different point on the y-axis. Make sense? Be able to use these plots, okay? I will fill these in for first order, and then see if you can do it, and then check your work. For these integrated rate laws, the units on the rate constant are going to be consistent for 0 order, first order, and second order. We can go through and do a unit analysis for each of these to determine what the units on K would be. Again, not very invigorating, so we will skip to the highlights here. For a first order reaction, and this is what you would essentially be doing, working through the units. Set everything equal to the rate constant, substitute in the units, and what you should end up with for the units on K for a first order reaction are inverse seconds. So if you know something is a first order reaction, and you're working with an integrated rate law, units are always going to be inverse seconds. For second order, we're going to have inverse moles per liter times inverse seconds. And then for 0 order, we're going to have moles per liter times inverse seconds. I actually like doing unit analysis. So I know no one else really does, but it's cool to not do it. Okay. Questions on it? Yeah. Yeah, Thursday, yes. So again, what we're covering today, and I think we're going to finish, will be on the exam on Thursday. In your recitation, Jennifer Stebeck sent out like this really long list of things to do ahead of the exam. It's in your announcements. Make sure you go through and do all of those things. If we have time on Wednesday, maybe we'll try to do the lockdown browser and make sure everyone's lockdown browser is working. But we'll see. I don't actually know how to do that myself, so I might need to do some digging. Okay. Half-life. We are almost done with section 14.3 here. Half-life. This is just a special instance of an integrated rate law, okay? So the special instance refers to the time required for a reaction to reach half its original concentration. And so essentially what that's saying is that the concentration at some time t is equal to 1/2 its initial concentration. Okay? This is, other than this part right here, there's nothing else special about a half-life. We will see it come back when we talk about nuclear chemistry. We talk about half-life decays. They're all first order when we're doing nuclear chem. So you'll see it come back, but it's just a special instance of concentration. Okay? So we can go through, and we'll do this one, for a first order reaction. I've rearranged that so that we have natural log of A at time t over A initial. And I should write this out here. This is just a rearrangement of ln of A at some time t equals minus kt plus ln of A initial. All right, so there's some rules for logs that go in here. When you are subtracting two logs, you actually can divide them. Remember, this might be a thing you don't recall, but maybe you do. But that's how we get from, the rule of logs is how we get from this equation to this equation. Okay, I'm going to write that. You can look that up. Okay. So once we've rearranged our first order integrated rate law to look like this, what we can do is plug in this equation where A at time t is equal to 1/2 the initial concentration. That's this. Okay. We can plug that into here. And we end up with this equation. So equation 1, 2, we end up with equation 3. The other thing to note here is that I've given our time a special subscript, so T1/2, signifying half-life. Okay. So if we look at this fraction, A sub 0 over 2 divided by A sub 0 is simply 1/2. Okay? So then we can get to equation 4. So we have the natural log of 1/2 equals minus some rate constant k times t at 1/2 the initial concentration. And ln of 1/2 is a constant. And that is going to be equal to 0.693. Okay? So to isolate T1/2 on one side of the equation, we divide both sides by k. Oh, ln of 1/2 is minus 0.693. And we end up with this for the half-life for a first order reaction. So what does this mean? The half-life is only dependent on the rate constant. It doesn't depend on the initial concentrations of material. Okay? For zero order and second order, that's not going to be the case. Right? But this is a nice equation. You just need to know the rate constant. We're not going to go through deriving second order and zero order, but for second order, we would end up with T1/2 equals 1 over the rate constant K times the initial concentration. I think these are also given on the exam, right? And then for 0 order, T1/2 equals initial concentration divided by 2 times the rate constant. Okay. I know I'm just showing equations, but does anyone have any questions on that? Okay. So the next set of slides asks you how you can verify if a reaction is first order. Right? And I've given some concentration and time data. And the way that we would go through and verify that is to plot it and then figure out what we would need to do to make it linear. And we could also start with plotting natural log of the concentration versus its time. So we could take the natural log of 0.1 and plot that versus time and go on down the table. And we would end up with a plot that looks like this. So here's some data points. They're a little hard to see. Okay, and fit it to a line. Y'all do line fitting in lab? No? Okay. Well, good. You'll get to that eventually, I'm sure. And what we see is that this is a linear fit. Okay? And the equation that's given from our slope, we can determine what? We can determine the rate constant. Yeah. So in this case, a rate constant is equal to, well, the slope is minus k, so minus k is equal to minus 0.0069, or k equals 0.0069. Okay. And this is really what people do when they're working on determining rate laws for different. And using the integrated rate law, you can actually predict concentrations after a given amount of time. So we'll go through and work this problem. So we want to calculate the concentration of N2O5 after 150 seconds of starting the reaction. So we need to use the equation that we got on the previous slide, which I believe was ln of A times T at time T, equals minus 0.0069 times T plus the natural log of the starting concentration. Okay. What's our starting concentration? .1. Yep. So at time 0, concentration of N2O5 is 0.1. And so we can plug that into the equation. And we're going to also plug in 150 seconds. Lots of zeros there on that one. I'm going to leave a couple off. We'll get minus 1.035 plus minus 2.3027. ln at sometime t then is equal to minus 3.34. but that's the natural log of the concentration. How do we get, mathematically, how do we get to, get rid of that natural log? Yeah.
You raise e to the power was s.
E to the power, yep. So we'll do E. So then we'll get concentration of A at time t, where we're going to say A, because I was sloppy here, equals concentration of N2O5, equals e to the minus 3.34, which is 0.0356 moles per liter. We could verify this, right? We can look at our data. We wanted to know 150 seconds in where what the concentration was going to be. And that's somewhere between these two data points, closer to the 200. So it needs to be less than 0.07 and greater than 0.025. And we're in that range, so seems reasonable. Okay. All right. Questions on that? Yes? Why is the K negative? In this case, our K is, we're going to leave the equation with the negative in this case because we want to have, our K is positive as I showed you on the previous slide, but we leave the negative in to represent this expression. This is showing up here. Does that make sense? Okay. And the other way to think about it is that it has to be negative because the plot goes down. Right? The slope is negative. Other questions? Go ahead, I'm going to have you calculate the half-life for this reaction. And let me write the equation back up here. That's supposed to be ln. That didn't look like an ln. Ah. Okay, take a minute there. What do we need to do to calculate the half-life? All right, so for this problem, we only need to know the rate constant, which is 0.0069. So T1/2 is 0.693 divided by 0.0069, and we end up with about 100 seconds. I've got sloppy here on my units. But you can go through and verify for me. Questions on that? One more before we go, because there's a I wrote feeling later, but I want to show you this one. Remember that I said that half-life is just a special circumstance of an initial concentration. You're half the initial concentration. What if we want the reaction to be 75% complete? Okay, that means that the concentration at some time t is only a quarter of what it was, 0.25 of what it was, right? Initially. So if it's 75% complete, 25% remains. So A at time t is going to be equal to 0.25 times A. Using this equation, ln of A at time t over A sub 0 equals minus k times t. You can plug in this equation. So A sub t is equal to 0.25 A sub 0. Rearrange and then solve for this equation to get the time required to be 75% complete. Not on the exam, so I'm not going to work through it, but I know you have homework problems on it. So let me know if you have questions.